the third time we have a guest speaker, David Vaccaro, going to join us in a few minutes. Great to see quite a few of you, despite the exams. So that's really good. Has anyone started the maths assignment yet? The 10th assignment for maths. Has anyone started? Okay, good. Right. At the end, there are a few Taylor series questions, and Taylor series quite fascinating. Quite fascinating.
Hi, Vlad.
Ah, hello.
How is everybody? Shall I share my screen?
Oh yeah, that would be great. Yes, we can hear you, see you.
Super. I heard you talking about Taylor series.
Yeah, just said that it's fascinating.
Let's try and oh, if you can make me host, I can share my screen.
Oh yes. Okay.
Well, let's hope we can reach the Taylor series towards the end. I'm sure we will. So in most of these sessions, I think most people have kind of communicated via the chat. So this is just a little puzzle to begin with, just to sort of wake people up, see who's here. So what comes next in the following sequence? So there's a sequence of numbers here, and your task is to figure out the term-to-term rule. So if you can spot the pattern, then put what you think is the next number into the chat. So we've got 1, 11, 21, 1,211, 111,221, 312,211, and then I guess that is 13,112,221. Okay, yeah, we've got a good suggestion in the chat. Well done, Edward. I'll just say those numbers away in a slightly different way. So we've got 1, then we've got 2 1s. Sorry, then we've got 1 1. Then we've got 21, or 2 and then a 1. Then we've got 1 2 1 1. And hopefully, in the way that I'm reading it, people can now see what's going on. This next number is 1 1, 1 2, and then 2 1s. Does anyone want to put in the chat and to describe what's going on with this sequence? Yeah, so it's the number of each number in the previous term. So what's happening here is the next number describes the previous number. So this number that I've just got here is 111, which we can think of as being 3 1s. Oops, my pen is enormous for some reason. Then it's 2 2s, So I write 2 2s, and then it's 1 1 at the end. The next number describes the previous one. So the missing number will be 1 1, then 1 3, then 2 1s, then 3 2s, then 1 1. So partly that was just a warm-up, but there is a little bit of a moral there. The moral there is, yes, you will meet some common sequence types, arithmetic series, geometric series, and so forth. But the important moral here is, you know, there's so many different ways of describing a sequence. So arithmetic sequences and geometric sequences are not the only one. Okay, question number 2. Again, we're still in brain warm-up mode. So it says, give infinitely many formulas for a sequence which has first terms 1, 2, 3, 4, 5. Now, my daughter, she's 5 years old, she's downstairs, and if I was to pull her up and I was to say to her, what comes next in the sequence 1, 2, 3, 4, 5, I've got no doubt that she would say 6. And obviously, one sequence that works is the sequence where the term number is just the number. Okay, so the first term in the sequence is 1, the second term in the sequence is 2, then 3, then 4, then 5. And of course, the sequence could continue like, sorry, an is equal to m. Now, of course, the sequence could continue like that, but there's no guarantee that it will. Okay, so what we're invited to here is to find infinitely many formulas which start in this way. I don't know if anyone's got any ideas, but one thing which we could consider is we could consider starting with this sequence that we know works, and then adding something which is 0 at each of 1, 2, 3, 4, and 5. And if you give it a moment's thought, this polynomial has clearly got roots 1, 2, 3, 4, and 5. So if I substitute in 1, 2, 3, 4, or 5 into this product, I will certainly get something which is 0. But obviously, if this is 0 at 1, 2, 3, 4, and 5, so is anything that I multiply it by. Okay, so I could multiply by, my pens are all of a strange size, but I could multiply by n squared, or n cubed, or sine n. Okay, in fact, I could multiply by any function here, so any function of n that I like. Okay, and so that obviously covers, you know, infinitely many. So what's the moral of that question? The moral of the first question was that there's, you know, many different types of sequence, and this kind of expounds on that fact in a little bit more depth. This shows that there's many sequences which start the same way. Okay, so just spotting a pattern in the first few terms is never enough to specify the whole sequence. Okay, so we'll see later that a very common thing which occurs in sequences is that the first few terms give you a clue, but you still often need to do some proof to establish what the formula for the sequence is. I know Dr. Chernov is very keen for us to get to Taylor series, so unless anyone kind of raises their hand, I will go on to the next question. So the next question is, I was quite keen to put this in because something that you do a lot of in when you study sequences and series is you go from the sequence to the series. So you learn how to add up add up the terms in a sequence. But I just want to look here at going the other way. So here we're not told the sequence, but we are told its partial sums. Okay, so we know that A1, so that's just the sum of the first term is 1 cubed. We know that the sum of the first two terms, A1 plus A2, is equal to 2 cubed, which is 8. And we know that the sum of the first three terms, I'll just make my pen a bit smaller, A1 plus A2 plus A3 is 3 cubed, which is 27. Now the question is, can we go from these given numbers, which are the sums, and the next sum would be A1 plus A2 plus A3 plus A4 is 4 cubed, which is 64. Can we go from those sums back to the sequence? So, for example, does anyone want to give a suggestion for what A2 is equal to? Well, we know that A1 is 1. And we know the sum of the first two terms, and I can see a lot of the chat getting quite busy, and lots of people are saying that A2 is equal to 7. Okay, because it's the difference between the new sum and the old sum. Does anyone want to give a suggestion what A3 is equal to? And again, the chat is getting busy. Well, we know that A1 plus A2, so the first two terms are 8. So A3 is going to be 27 take away 8. And the people that put 19 into the chat are correct. And similarly, A4, well, we can block off the sum of the first three terms, A1 plus A2 plus A3. We know that they're 27. 27 plus A4 is 64. And so A4 is 37. Now, what we've done here, and I would start any sequences question in this way. We've got some numerical evidence. We've got some numerical data for the first few terms in the sequence. But more importantly, we've got a method. So more importantly, we know that the sum of the first, we're finding all of these terms by subtraction. So we know that the sum of the first n terms is n cubed. But we also know that the sum of the first n minus 1 terms is n minus 1 cubed. So we can write an is n cubed take away n minus 1 cubed. And we can obviously cube this bracket using the binomial expansion. So we get n cubed minus 3n squared plus 3n take away 1. The n cubes cancel. So we get 3n squared take away 3n plus 1. Okay, so a neat little example there. The first two questions have had a moral. The moral here is that we can reconstruct a sequence from the sum by taking differences. Okay, any questions at this point? As I say, I'm keen to get on to a sort of discussion of Taylor series, so I'm going quite briskly. But does anyone have anything that they want to say at this point? Are people happy for me to continue? Put a thumbs up if you are. Yeah, we've got lots of thumbs up coming. Excellent. Okay, so question number 4. So part A says express 1 over n plus 1 as the difference between two fractions. Now, if I reverse engineer how I'm going to get a fraction like 1 over n plus 1 as a difference between two fractions, I've almost certainly used fractions with a denominator n and n plus 1. Okay, because they would multiply to make a common denominator of n plus 1. And there might be some constants on the top. If I combine the two fractions here, I get that, I'll skip the algebra, but I get a common denominator of n plus 1. If I combine the coefficients of n, I get a minus b. And if I look at the units coefficients, I get a. And now I just compare what I've got and what I want. So the units on the left is 1, the units on the right is a, so a is 1. I want this n term to disappear, so a equals b equals 1. So 1 over n plus 1 is 1 over n, take away 1 over n plus 1. Part B says, hence, find the sum of 1 over n plus 1 from 1 to n. So the hence is the giveaway. So I want to use the previous identity. So when n is 1, the previous identity tells me that 1 over 1 times 2 is 1 over 1 take away 1 over 2. And the previous identity tells me that 1 over 2 times 3 is 1 over 2 take away 1 over 3, all the way down to 1 over n plus 1 is equal to 1 over n take away 1 over n plus 1. Now, this summation sign is inviting me to add all of these up. And I invite everyone at this point to stare at all of these terms here, all of these fractions. And can anyone describe in the chat what happens when we add up all the fractions on the right-hand side? So we're adding up 1 over 1 take away 1 over 2. Then we're adding 1 over 2 but taking away 1 over 3. All the way down to adding 1 over n and then taking away 1 over n plus 1. Excellent. So when we add up, I was just checking the chat, the majority of the fractions cancel because the fraction that we're adding is what we were subtracting in the term above. So when we add everything up, we get that the sum from n equals 1 to n equals n of 1 over n plus 1. The only terms which are left are the first one and the last one, and that should have been a capital N. So we get 1 over n plus 1. What's the limit as capital N goes to infinity? Well, this final fraction goes away to 0. So we have that the limit as n goes to infinity of 1 over n equals 1 to n of 1 over n plus 1 is equal to 1. Okay, so this infinite sum was relative, well, I'm going to write easy in the sense that we know this infinite sum. Now, in part D, we're going to look at a much more complicated sum, the sum of 1 upon n squared. Now, this sum 1 upon n squared, around the 1750s, was an unsolved problem in mathematics. We'll see in a moment that this sum must converge, but some mathematicians in Basel in the 1750s posed the problem of saying, what does this sum 1 upon n squared actually converge to? And the exact figure was found by a mathematician, a very, very famous mathematician called Euler. And Euler was able to find the exact value of this sum. And I won't spoil it and tell you the answer, but it's got very surprising numbers in it. And it actually turns out to be a sum that is closely related to one of the most famous functions in the whole of mathematics, and something that you'll meet a lot at university. If we were to take the sum of 1 upon n cubed, okay, that would also converge. And so we could actually think of creating a function, and this function has got a name where this sum is, the function is called the zeta function. So, and the sum upon 1 over n squared would be zeta 2. The sum of 1 over n cubed would be zeta 3, and so on. In fact, zeta s is the sum from n equals 1 to infinity of 1 over n to the s. So this sum that we're asked to consider in part D, the sum from n equals 1 to infinity of 1 over n squared, is hard. Okay, there's no easy answer for that sum. But what I'm going to revisit now is an idea that I spoke a little bit about last week, of this idea of finding upper and lower bounds. So what I can do is I can use the sum which is easy to find upper and lower bounds for the sum which is hard. Okay, so let's look at these two sides. So, and I think it always makes sense to write out the terms. So the sum upon 1 over n squared is 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so forth. Now, question 1, how can I make this sum bigger? Well, I can make this sum bigger by making the denominators of the fractions smaller. So when I have 2 squared, which is 4, a larger fraction would have a smaller denominator, which would just be 1 times 2. When I had 3 squared, a smaller, and 3 squared is 9, a smaller denominator would be 2 times 3, which is 6. And then 4 squared, I can make the fraction larger by replacing the 4 squared, which is 16, by 3 times 4, which is 12. And so what do I have here? Here, I just have this same sum that I had before, the 1 over n plus 1, and I know that this yellow sum converges to 1. So the sum of the reciprocal of the squares is less than 2. Okay, now I need to go the other way, and I need to try and get something which is going to be smaller than my sum. So where I had 2 squared before, I could replace the 2 squared by a larger denominator, which would be 2 times 3. Where I had the 3 squared before, I could have a larger denominator, which is 3 times 4, and then I've got 1 over 4 times 5. And now I'm almost done, because this orange set of orange terms here is the same sequence, but without the initial term, the 1 over 1 times 2. So whereas before everything summed to 1, now I'm not getting that initial term of a half, so everything is just summing to a half. Okay, so I haven't done as much work as Euler. Okay, but what I do know now is that the sum of the reciprocals of the squares is somewhere between 1.5 and 1. Okay, and what you'll find is that Euler, in order to find the value of this sum, got better and better estimates, and then sort of recognized that it was close to a moderately famous number. Okay, so those questions were on sort of introduction to sequences. Any questions at this point before I continue? Okay, good. Next couple of questions are on arithmetic sequences. Now, I know we're keen to get on to Taylor series, so I'm just going to do one of question 5 and 6, because I think arithmetic sequences are relatively familiar. I might come back to it later if I've sort of finished with the Taylor sequence. To make it slightly interactive, I'll just take a vote. So if you prefer the look of question 5, put the number 5 into the chat. If you prefer the look of question 6, put 6 into the chat. And by prefer the look of, choose the one which you think looks harder. Okay, excellent. So we've got lots of votes for 6. So it says, if a squared, b squared, and c squared are an arithmetic sequence, show that 1 over b plus c, 1 over c plus a, and 1 over a plus b is also an arithmetic sequence. So what does it mean to be an arithmetic sequence? Well, it means we're going up by the same amount each time. So we're going up by d each time. So what I can write down is I can write that b squared minus a squared is equal to d. And I can also write that c squared minus b squared is equal to d. And if it's useful, I can add those two together, and I know that c squared minus a squared is equal to 2 times d. Okay, so a squared, b squared, c squared is an AP, implies these relationships. Now, what I want to do is show that 1 over b plus c and 1 over c plus a and 1 over a plus b are an arithmetic sequence. So I also want to show that they have a common difference. So I want to compare the differences. So first of all, let's look at 1 over c plus a, take away 1 over b plus c. So this is the difference between these two terms. And this is equal to b plus c, take away c plus a over a common denominator of C plus A, B plus C. And the C's cancel, and so we get B minus A over C plus A, B plus C. We now want to look at the difference between these two terms, the 1 over C plus A and the 1 over A plus B. Okay, and let's just do a little bit of a cute trick. Okay, obviously we can do the algebra, but notice that we've just got the same types of terms. So C has become A has become B, and B has become C in the question. Yeah, so where the C was before, we've got an A, where the A was before, we've got a B, where the B was before, we've got a C, and so on. So we can just do the same cyclic reordering in this simplified expression over here, and we get C minus A over A plus B, C plus A. Sorry, C minus B. Okay, now that little trick wasn't particularly useful in this example because the algebra was quite easy. But in future work, especially for, when you do complicated physics, there's lots of, physicists talk about symmetry a lot. So there's lots of symmetric expressions where you sometimes find yourself repeating the same calculation. So what we really want to do is show that these two expressions are the same. And our life would be much easier if we had a common denominator. And I deliberately didn't open the denominators because that would get things complicated. But I can see that I can make a common denominator if I just replace the bracket that I'm missing. So at the moment, I've got C plus A and B plus C, but I don't have a B plus A. And if I was to multiply by B plus A, I would just get B squared minus A squared over A plus B, C plus A, B plus C. And if I was to multiply by the missing bracket on the bottom here, my B plus C, again, I would get difference between two squares, C squared minus B squared over A plus B, C plus A, B plus C. But that's quite nice because we know that the difference between these squares are in both cases D. So we've got D over A plus B, C plus A, B plus C. And here we've got D over A plus B, B plus C, A plus C. And so we've got that 1 over B plus C, 1 over C plus A, and 1 over A plus B also have a common difference. Okay, so nice question on arithmetic progressions. And if everyone's happy with that, oh, there's a smile for liking the trick. Okay, good. As I say, the trick wasn't particularly useful in this example because the algebra was easy, but being on the lookout for symmetry will be a good thing to do in the future. Okay, on to geometric sequences and series. So this is adapted from a math paper. So it says f of x equals 4x plus 1, and it asks us to find an expression for f of x. Okay, now we know how to compose functions. So this is the same as 4fx plus 1, just replacing where I had x before. I'm now putting in my packet fx, but fx is 4x plus 1, so this becomes 16x plus 5. And now they want me to play the same game. So they want me to find f of x, f of x. So we want to apply f to the previous part. So we want to do f of 16x plus 5, which gives me 4 16x plus 5 plus 1, which is 64x plus 21. It now says find formulas for the sequence an and bn, which are defined such that the n-fold composition of f is done n times. Okay, so we've got, this is the two-fold composition. This is just the one-fold composition. So we've got the start of each sequence. So the an sequence starts 4, 16, 64, and the bn sequence starts 1, 5, 21. Okay, let's do an easy thing first. Okay. Does anyone want to suggest a formula for the an sequence? So stare at those numbers, 4, 16, 64. What do we think is the next number in that sequence? Yeah, and lots of people in the chat are saying 4 to the power n. Okay, slightly more thought required. What do we think the bn sequence is? Okay, okay, so we've got 4 to the n minus 1 plus 1. That doesn't quite work because it's not one, these are not one more than a power of 4. So, okay, so there's two. Okay, there's two sequences. An, we recognize the sequence, it's 4 to the power n. Can anyone give me a good explanation of why an is 4 to the power n? So imagine you're in your math paper, you want to say an is equal to 4 to the power n because what? Well, let's think about what happens to the x coefficient each time. We end up multiplying by 4, okay? Now, what's the best way of writing this? So f of x is f of, this is n times, is f applied to f of x n minus 1 times. But we know what that is. That is just an minus 1 plus bn minus 1. So if we use our f function, we've got that anx plus bn is equal to 4 an minus 1x plus bn minus 1 plus 1. So we've got 4 an minus 1x plus 4 bn minus 1 plus 1. Okay, and what we can see if we just look at the x coefficients, an is equal to 4 an minus 1 and Bn is equal to 4 Bn minus 1 plus 1. Okay, but this first one shows An is a geometric sequence with common ratio 4. Now, to find the Bn sequence, there's two things you can do. There's two methods of proof that suggest themselves. So method of proof 1 is let's try and really keep track of what happens to the Bn sequence. So B1 is equal to 4. B2 is 4 times B1 plus 1. So that's 4. Sorry, B1 is 1. B2 is 4 times B1, which is 4 plus 1. B3 is 4 times B2, which is 4 times 4 plus 1, but then plus 1, which is 4 squared plus 4 plus 1. So what I've done in this first method is I've resisted the temptation to actually make the number, so to make the numbers 1, 5, and 21, but instead looked at how these numbers were formed. So this 21 is well thought of as, is better thought of as 16 plus 4 plus 1. And then B4, we multiply by 4, so we get 4 cubed plus 4 squared plus 4 plus 1, and so forth. So what is happening in the sequence Bn, we can see that it's not a geometric sequence, but it's a geometric series. Okay, and we know the formula for the for a geometric series. It's the first term multiplied by the common ratio to the power of n minus 1 over the common ratio minus 1. And once I substitute in the first term of my sequence is 1, the common ratio is 4, I get that Bn is 4 to the n minus 1 divided by 3. Okay, does that work? So if I start at if I consider the number 64, that's 4 cubed. Bn should be 4 cubed take away 1 divided by 3. And 64 take away 1 is 63, divided by 3 is 21. And this points to a second method. Now, in the chat earlier, no one spotted that formula for Bn. Okay, but maybe if people are on their own or staring at it longer, you might guess that method, that formula. So method 2 would be to guess Bn equals 4 to the power n minus 1 over 3. Now, this is true when n is equal to 1, because B1 is equal to 4 to the power 1 minus 1, which is 3 divided by 3. So this, if you'd spotted this formula, 4n minus 1 over 3, that works for n equals 1. But let's assume that it worked for some later value. So let's assume bk is equal to 4k minus 1 over 3. Now, at the moment, the only value of k we know this is true for is k equals 1. But what we know is we've got a relationship that tells me how bk plus 1 is related to bk, because it's 4bk plus 1, which is now 4k minus 1 over 3 plus 1. 4 times 4k is 4 times k plus 1. Take away 4, we make a common denominator and write this 1 as 3 over 3. And we get 4k plus 1 minus 1 over 3. Now that's interesting. So what we've shown here is that if bk is equal to 4k minus 1 over 3, that implies that bk plus 1 is 4k plus 1 minus 1 over 3. And we know that b1 is 4 to the 1 minus 1 over 3. Now, these two facts together give me the correct formula for bk for every k, because the formula is true for b1, but this little bit of code tells me that if it's true for b1, it's true for b2. But then if I repeat that little bit of code, this little bit of code tells me that if it's true for b2, it's true for b3. So what we can say here is bn equals 4n minus 1 over 3 for all n. Okay, now, the more maths you do in this type of area, the more familiar you'll get with this second method. Because it turns out that in many circumstances, this is the best way to go, to look at the early cases and find a formula that you think does work, and then prove that it does indeed work. That's often a slightly easier process than coming up with something ingenious like this. Okay. Now, I don't know if I've taught you something new just now. Does anyone know the name of this type of proof? Yeah, good. It's a proof by induction. If you've ever done any sort of maths Olympiad papers, things like that, you won't have gone very far without meeting a proof by induction. Okay, was everyone happy with that question? Okay, super. Now, you guys are all young, and fresh-faced. Well, none of you are showing your video, but you're all sort of fresh-faced and young-looking. I'm starting to go a little bit grey, okay, because I have to pay off a horrible thing called a mortgage. And for many people, okay, paying off a mortgage is the sort of most important sort of time in their life when they meet a geometric sequence. So this question that we're about to do is one that you won't just meet in your studies, but you will meet in real life as well. So let's look at what the question says. So the question says, let me just scroll over to it. Brian takes out a mortgage for £300,000. So a mortgage is like a debt. And when you take out a debt, the person who is lending you the money adds what's called interest. So they make you pay a little bit more back each year. And in this world, interest is being added at 5%. Okay, so Brian's initial debt is 300,000. 5% of 300,000 is 15,000. So at the end of the year, his debt goes up to 315,000. But mortgage providers and people who make debts don't like this idea of a debt just getting bigger and bigger. Okay, so Brian is instructed to pay some money, and then he pays £30,000. So we now take £30,000 off the debt, and that takes us down to 285,000. Okay, so this is time 0. And then this is time 1. Okay, so notice 2, and this 315,000 is just like an instant. Okay, so after 1 year, Brian owes 285,000. At time 2, we would add 5% interest, so we would multiply by 1.05, and then we would take off 30,000. Now, the debt obviously shrinks. Okay, so Brian's debt is going down each year, but what else is happening to the amount that Brian pays off? So in the first year, the debt has gone down by 15,000. In the second year, does the debt go down by 15,000 again, more than 15,000, or less than 15,000? Oh, there's a question here. Why does he pay the installment before? Why does he pay the installment after the interest is applied? Wouldn't it be lower? Yeah, I've simplified this a little bit. So in reality, interest would be added monthly, and installments are monthly. I've just assumed that the interest is added first because the interest is added on the sort of previous debt, and then the installment pulls it down. In a question like this, it does need to specify. The important thing in a question like this is just specifies the order in which things happen. And I've just made sure that I'm clear that the interest is added first and then the debt is paid off. Next comment in the chat, though, is that in the second year, the debt goes down by more than 15,000. Okay, so that it goes down more because the debt has gone down, less interest is added. So what that means, the way in which he pays off the debt is slow to begin with, but then gets faster. Because towards the end of paying off the mortgage, you're just paying off at £30,000 a year because no interest is being added. Okay, so the shape of the debt over time is concave down. Okay, one way we could proceed with the question is to proceed with the numbers 300,000, 1.05, 30,000. But a really, really good tip, and this is sort of slightly different to the tip that your maths teachers might have given you in other contexts, but in a question like this, I would strongly advise not using the numbers because the numbers are going to get messy. But just as in the last question, it's better to keep track of the structure of what's happening. And so to just look at, instead of numbers, let's call these things letters. So I'm going to say the initial debt is M for mortgage. The interest, I'll put R for interest rate. And the amount that he's paying off, I'll call D for difference. And let's look at this generally. So at time 0, the mortgage is M. At time 1, we add interest to the mortgage and then take away D. Okay, so the function which takes me from one time to the next is multiplying by R and then taking away D. Okay, so it's actually quite similar to the last question, which was iterating a linear function. In the last question, we were multiplying by 4 and adding 1. Here, we're multiplying by R and taking away D. So let's multiply by R again. So that gives me MR squared take away DR. So this is my time 2. and then I need to take away R. Now time 3, I multiply by R, so I get mr cubed, and then I take away dr squared, so I take away d, then I multiply d by r, so I've got dr, and then I take another installment of d. So at time n, the debt is mrn, take away d plus dr plus dr squared plus dr to the m minus 1. And I'm just careful that I've got one fewer term than the year number. Now, this formula should make sense to people, okay? Because the MRN, you know, let's put your economist hat, that makes sense because that's just the initial mortgage of M, but then interest has been added R times. And every time we add interest, we just multiply by an extra R. But now, if we think of the installment payments, the most recent installment payment is just D. And that's just been added at the beginning of the year, so no interest has been added on it. The interest paid, the installment that he paid a year ago, that was 1 year in the past. And what happens to the debt each year is it gets multiplied by R. The installment that he paid 2 years ago, it's as if interest has been added on that installment twice. And then the installment that he added at the end of year 1, it's like interest has been added n-1 times. Okay, so we've got MRN. We've now got this bracket, but this bracket is just a geometric series. So we get drn minus 1 over d minus 1. Okay, and the question says, after how many years does it take Brian to pay off the mortgage? Okay, so we want this to equal 0. Now, in the real world, of course, it won't necessarily be paid off at exactly the end of the year, but this is good enough. So we want drn minus 1 over d minus 1 to equal mrn. And now we want to find n, so let's multiply both sides, well, expand the brackets on the left, multiply both sides by d minus 1, so we get m d minus 1 rn minus, md minus 1 rn. We want to find n, so if we gather all the terms with rn together, we get that, what am I doing? D plus m minus md Rn is equal to D. I'm getting terms that I'm not expecting. This should be R minus 1. That's what makes no sense. So this is R minus 1. This is R minus 1. Sorry. And now we get D minus, we get M plus D minus Rm is equal to D, and then we get Rn equals D over D minus Rm minus plus M. which is the same as D over D minus RM minus M. Okay. Sorry, I struggled with that algebra a little bit. I'm starting to get tired towards the end of the day. Can anyone explain to me why this denominator, having struggled with the algebra, it's a good idea to do the sanity check. Okay, what sanity check can I do which tells me that this formula for that this denominator looks right? So when would we get a singularity? We can see here that we would get a singularity if D was equal to RM minus M. Now let's look back at Brian's mortgage. Notice that in the first year, £15,000 of interest was added, and the only reason the debt went down was because he was paying £30,000. If he'd only been paying £15,000, the debt wouldn't have gone down at all. Okay, so if the annual payment is the same as the increase in the mortgage after the interest has been added, then you'd never pay off the mortgage. So this denominator looks right. How would we now find the value of n? So how would we now find out the time? Well, we want to take logarithms, okay, and we want to take logarithms base r. So the time to pay off the mortgage is logarithm base r of d over d minus rm minus plus m. Okay, and now we would just need to plug in the values. R equals 1.05, D equals 30,000, and M equals 300,000. Okay, let's just, before I figure out that number, can people put in the chat what they think will be the answer just by eyeballing it? So the mortgage is £300,000 and he's paying £30 a year at 5% interest. Put in the chat what you think the answer will be. And I will evaluate it. Always a good sort of skill with this for a physicist to get a sort of ballpark figure. So do you think it's going to be 5 years? Do you think it's going to be 20 years, 100 years? I'm just putting in the figure. I'm hoping to see lots of guesses into the chat. Okay, and the answer came out as 14.2 years. Okay, why does that make sense? Well, if there'd been no interest, he would have been paying it off in 10 years because 10 lots of 30,000 are 300,000. We've already seen that the worst possible year was the first year, where the debt only went down by 15,000. So it's going to be less than 20. It's going to take him less than 20 years to pay off. Okay, so somewhere between 10 and 20 years seems sensible, and it turns out to be 14,000. Okay, any questions about that question? Everybody put a thumbs up if everyone is happy. Yeah, good, lots of thumbs up. I'm just going to stop sharing for a second. And I'm going to share my screen. Okay. Other software packages are available. Okay, but as you can imagine, as a physicist, you know, and when you go to university, this formula that we've got for the length of time, you know, to pay off a mortgage is exactly the sort of formula that you might get out from a sort of physicsy type, you know, situation. And a natural thing to do is to try and look what happens when you vary different parameters. Okay, and a really good thing to use to investigate that sort of thing is a computer. So I've just plonked in that formula. So that's the formula for the time to pay off, and I've substituted in different parameters. Okay, and this is exactly the sort of thing that sort of, you know, when you take out a mortgage, the person in the bank will kind of show you. What you can see is if you reduce the annual payments, the length of time to pay off the mortgage increases. As you get close to 15,000, which is that magic point where you're just paying off the debt, it becomes longer and longer to pay off, you know, to pay off the mortgage. One thing you could do is you could plot the length of time to pay off the mortgage as a function of the installment. Okay, and you can see that as the, and you know, this is, I'll just, what does this graph show? You know, this shows exactly what you would expect, that as you increase the annual payment, the length of time, which is the y-axis, decays. As you get close to 15,000, and I'll just put the plot range full again. The length of time to pay off the mortgage clearly just like goes off to infinity. Okay, and so a computer, a spreadsheet, a programming environment like this would be a good way to investigate that sort of function. Oh no, we've only got 20 minutes, and we want to do Taylor series. Okay, so of the more advanced sequences, I'll do the first one, and then I'll try and rattle through this one quite quickly, and then hopefully we'll have time for a bit of Taylor series. Okay, so find a positive number phi which satisfies the relationship phi squared equals phi plus 1. So we can solve the quadratic equation, and the positive root of the quadratic will be 1 plus root 5 over 2. Okay, now what do we know? Okay, we know that 1 can be written as 2 over 2. We know phi can be written as 1 plus root 5 over 2. But we also know that phi squared is these two numbers added together. So phi squared is 2 plus 1, which is 3, plus root 5 over 2. Now, how can I continue the sequence? Well, I know that phi squared equals phi plus 1. If I multiply by phi, I get that phi cubed equals phi squared plus phi. So to get phi cubed, I can add these two fractions together. So 1 plus 3 is 4, and root 5 plus root 5 is 2 root 5 over 2. And that's phi cubed. But now you can see exactly what's happening, that the next power of phi is the sum of the previous two. So the next power of 5 would be 3 plus 4, which is 7, as a number. And then we add the 2 root 5. So we get root 5 plus 2 root 5. So we get 3 root 5 over 2. So what we can see is that we get a number, a sequence of numbers, which starts 2 and then 1, but then where the new number is formed by adding the previous two. So it goes 2, 1, 3, then 4, then 7, then 11, then 18. Then the root 5s go 0, then 1, then 1, then 2, then 3, then 5, then 8. Okay, and both this sequence, we'll call it Ln, satisfies Ln plus 1 equals Ln plus Ln minus 1. And this second sequence, which we'll call Fn, satisfies Fn plus 1 equals Fn plus Fn minus 1. Pub quiz knowledge, which I imagine everyone here knows. What do we call this sequence? The Fibonacci sequence. Now, someone earlier got very excited in the chat. So Thomas commented that when I got this number phi, that it was the golden ratio. But now this is doubly exciting because we've got the golden ratio and the Fibonacci sequence all in one question. So we've got that the golden ratio to the power n is some sequence of numbers, which I'll call Ln, which are actually like the Fibonacci numbers' little brother. They're called the Lucas numbers. And then we're adding a Fibonacci number times root 5, all divided by 2. Now, any offers for how we can get rid of the LNs? Well, there's another number I could have played the same trick with. I could have played the same trick with the other root of the original quadratic. And the only way the other root of the original quadratic differs is that it's got a negative root 5. But I would get the same addition as before. So the other root raised to the power n is the Lucas number minus the Fibonacci number over root 5 divided by 2. And to eliminate the Lucas numbers, I just subtract. And then I get the Fibonacci numbers times root 5. So I get the Fibonacci number is phi to the power n minus phi hat to the power n all over root 5. But phi we know is the golden ratio, 1.618. Phi hat turns out to be negative 0.618. So in particular, phi hat is less than 1. So what happens to this term? As n becomes large. Well, we know from geometric series that a term becomes really small if a geometric sequence becomes really small if the common ratio is less than 1. Okay, so this term goes away. So to a very good approximation, the Fibonacci numbers, they're not a geometric sequence, but they're almost a geometric sequence, and their common ratio is the so-called, is close to the golden ratio. And this proof, this question provides a very, very nice proof of that. Okay, so give a thumbs up if you like that last question. I think it's an absolute cracker. And now we've got a chance to do a little bit of Taylor series. Now, one word of warning to everybody: my laptop battery is slowly decaying, and I haven't brought my charger home from work. So if I suddenly just like cut out and disappear, that's what's happened to me. But it will be mid Taylor series. Okay. So let's have a look at Taylor series. Now, in the note, in the sheet that I wrote, I did it from one perspective, which was from sort of like looking at almost constant acceleration equations. I'm going to do it in a slightly different way. So I'm going to pick one of our favorite functions. I'm going to pick e to the power x. Now, e to the power x is categorically not a polynomial. Okay, so if I write any expression like this, this expression is not going to be true. But what I'm going to do is I'm going to make the very bold step of saying that even though I can't write e to the x as a polynomial, that I can write it as an infinite polynomial. So I'm going to assume that I can write it as a power series. Okay, let's just assume this is true, and we can also assume that we can do normal sorts of things. Does anyone want to give me a suggestion of how I can find the value of A0? So in other words, I want to find the value of A0. So I want to get rid of all of these terms. Good. I can plug in x equals 1. So if I put x equals 1, I get e to the 0 equals A0, and all the other terms die. So A0 is equal to 1. Okay. Any idea how I can get A1? Now, the problem with my A1 is if I set x equals 0, I kind of kill it. But I can do something very clever to get rid of this x term. What can I do very clever? I can differentiate. And yes, I did mean x equals 0. So what I'm going to do is I'm going to differentiate my original expression for e to the x, and I get e to the x is now equal to a1, x squared differentiates to 2x, x cubed differentiates to 3x squared, and x to the n differentiates to n, x to the n minus 1. Now what trick can I play? And it's an old trick. What trick can I do to find x1, to find a1? Well, just like before, I want to get rid of all of the remaining terms, so I can just put x equals 0 again, and I get e to the 0 equals a1, and I get a1 equals 1. But I can keep playing the same game now. I can differentiate and then set x equals 0. So if I differentiate again, I get e to the x. the a1 goes away, the 2a2x becomes 2a2, the 3a3x squared becomes 3 times 2, which is 6a3x, and this term becomes n minus 1 an x to the n minus 2. Now when I put x equals 0, I get e to the 0 equals 2a2. So what does a2 equal? A2 equals 1/2. And then I can repeatedly play that game again. And you can see that the next time it would start with e to the x is equal to 6a3 plus stuff. And so a3 is equal to 1/6. Now we can do a little bit better. We can keep track of what happens to the x to the n term. So when I differentiate, I pick up a factor of n. When I differentiate again, I pick up a factor of n minus 1. In order to get rid of all the x's, I need to differentiate n times. And if I differentiate e to the x n times, I just get e to the x. If I differentiate a to the n, x to the n times, I get n minus 1, n minus 2, all the way down to 1, which is n factorial an. And then I'll get higher order terms. I'll get an n plus 1 term with an x, with some number, which doesn't particularly interest me here. And the reason this number doesn't interest me is that I can kill it by setting x equals 0. So I get 1 equals n factorial a to the n. So a to the n is equal to 1/n factorial. So we get this lovely relationship, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial. Now let's just do, something interesting. Let's differentiate. So if we differentiate e to the x, we get e to the x. What happens if I differentiate 1? Well, it just differentiates to 0. What happens if I differentiate x? It differentiates to 1. What happens if I differentiate x squared over 2? I pick up a factor of 2, which cancels with the 2 from the 2 factorial, and I get x over now 1 factorial. When I differentiate the x cubed, I pick up the 3, which takes away the 3 from the 3 factorial. So 3 factorial just becomes 2 factorial. And then this term becomes x to the n minus 1 over n minus 1 factorial. But what you can see is I get exactly the same power series repeated, which is quite nice. So we can see that that works. Okay. A really good exercise for you is e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus xn over n factorial. E to the y is equal to 1 plus y squared over 2 factorial plus y cubed over 3 factorial, and so on. See what you get when you multiply those two things together. Okay, and it'll be a nice exercise, but you should be able to prove that if you multiply those right-hand brackets together, that e to the x times e to the y is equal to e to the x plus y. Oh my God, is my battery going to survive this next bit? So, you know from other sheets that we've done that sine to the x is less than x. for x bigger than 0. Okay, now I'm going to draw this sine curve, and this is y equals x, this is y equals sine x. I'm in a race against time and my battery. Okay, what I'm going to do now is I'm going to integrate. So obviously the area under this sine x curve is less than the area under the line y equals x, and I'm going to do this between 0 and x. So the integral from 0 to x of sine t dt is less than the integral from 0 to x of t dt. Sine t integrates to negative cos t, and I evaluate between 0 and x. T integrates to a half t squared between 0 and x. So I get negative cos x minus 1 is less than 1/2 x squared. And then if I rearrange, I get that cos x is bigger than 1 minus x squared over 2. But I know that cos x is less than 1. Okay, now my battery is critical. What do you think I'm going to do next? So I started with an integral for sine x, and I've ended with an integral for cos x. And I got that integral by integrating. Okay, so what I'm going to do now is integrate this inequality for cos x. So the integral from 0 to x of 1 minus t squared over 2 dt is less than the integral from 0 to x of sine t dt. And the upper integral is clearly just x. But the integral of 1 minus t squared over 2 is t minus t cubed over 6. And let's evaluate between 0 and x. The integral of of cos t is sine t. And that's between 0 and x. And we get less than x. So I get this inequality, sine x is less than x, but it's bigger than x minus x cubed over 6. You should recognize this idea as having what we've mentioned in a few previous questions of having an upper and lower bound. Now, what do you think when I get when I integrate again? Well, when I integrate again, I'll tell you that I get cos x is again bigger than 1 minus 1/2 x squared, but I improve the upper bound and it becomes 1 minus 1 over 2x squared plus 1 over 24 x to the power 4. And if I improve the inequality for sine x, it remains bigger than x minus x cubed over 6, but becomes less than x minus x cubed over 6, which is 3 factorial. But the next term becomes x5 over 5 factorial. Now, if I continue forever, and that you should do this as an exercise, these power series get larger and larger, and you can see that these power series become better and better and better approximations. And what you actually end up with is Taylor series for cos x, and you can hopefully verify that this is the same thing that you would get if you used my same method for e to the x earlier. So you end up that cos x only has even powers of x. That makes sense because it's an even function. Sine x only has odd powers of x. That makes sense because it's an odd function. And we get e to the x has got all the different powers of x. This could end up being very dramatic because this is now a imagination test, and my battery and the time are pretty much running out. So these are Taylor series, okay, and these are the Taylor series for ex, cos x, and sin x. Okay, and this is just scratching the surface of Taylor series. You can tell from Vlad's smile that he mentions them, of how sort of important they become. But now here's a little imagination test, and actually this goes back to the same mathematician I mentioned earlier with the Basel problem. This goes back to Euler. Hopefully you can see that the Taylor series for e to the x, the Taylor series for cos x, and the Taylor series for sin x all have the same type of terms. Okay, they all have a term x to the n over n factorial. Okay, the only difference is that when that comes up in cos, that x to the n over n factorial, if it's even, it will be in the cos x Taylor series. If it's odd, it will be in the sin x Taylor series, and we get these alternating signs. And I think this is actually a lovely, lovely place to stop. But Euler, through other methods, but you can do it through these Taylor series, found a wonderful formula that linked E. So from these Taylor series and the fact that they've got similar terms, can you get a formula that links e to the x in some clever, complicated, maybe complex, maybe that was a hint, but some interesting way that connects e to the x to cos x and sin x? And I will leave that hanging out there as a challenge. And if that doesn't get you excited at Taylor series and makes you feel that Taylor series are exciting mathematically as well as exciting physically, then nothing will. Okay, my battery is at 6%, so I think this will end very, very soon, so I might disappear. But does anyone have any questions, comments, suggestions, either about that last Taylor series exposition and that final challenge, or any other parts of today's webinar? No comments. But we've done good. We've got a formula for the Fibonacci numbers. We've seen the Fibonacci numbers related to the golden ratio. In this question, we've seen the exponential function related to cos x's and sin x's. And we've learned how to pay off a mortgage. So we've done lots of fun maths.
Thank you very much. This was great. I really enjoyed listening in. Thank you very much, David.
You're welcome. So I'll send people the PDF of what I've written. I've also got a PDF of the questions, and there was a couple of questions. There was a couple of questions that we didn't end up going through, but people can have a look at those in their own time.
I'm publishing the PDFs on our normal whiteboard. So if you go to the whiteboard, you will see the PDFs. But also I'll send them through in our chat.
Super. Well, I hope everyone enjoyed it. I'm going to go down my door. There was a little bit of noises off. Yes.
All right. Thank you. Thank you so much. See you next week, everyone.